Hi, welcome to the next session of the course VLSI Physical Design Automation. In today's session, we are just trying to see that what is the relationship between the graph theory and a VLSI physical design or the VLSI design. So, we are going to see that how the graph theory can be implemented, how the graph theory can be adopted for the VLSI design. That is the main concept we are going to see it in the today's class, today's session, and also followed by we will see that what are the different types of graphs are available and how come that particular graphs can be get defined and in what way we can able to effectively use the same for the VLSI design. Let me consider a basic circuit, a basic logic circuit. I am just considering one basic logic circuit. So I have one AND gate. There is no logic here. I am just drawing one example gate here to see that how we can implement or how we can represent the same in terms of the graph. Let us assume that this is the basic circuit. Here I have an input A, input B and C and D, and this can be output Y. Now, the so-called logic gates, what is it available over here, that I will call it as logic gate 1, and this is logic gate 2, and this is logic gate 3. So, I am not going to see that what functionality it is. According to the functionality, it is called your AND gate. This is your AND gate, and we have one NAND gate and one more AND gate is available, right? So, I am not going to looking into what functionality it is. I am just looking this as a circuitry, as given a logic circuit which we are going to get implement in our IC. So now, in order to represent this particular logic circuit, basic circuit in terms of the graph, it is more easy for us to represent. How we can able to represent over here? While you are converting this particular logic circuit into a graph, okay, so I am not going to concerns about this particular input, so I am just going to omitting this A, B, C, D and as well as the Y, and also I am going to see that I am going to consider only that the logic cells of 1, 2 and 3. See that I am just telling logic cells, I am not telling that it is a gate. So I am just going to represent the gate hereafter in terms of what? Cells. Okay. And now we can able to consider only the cells. So I can able to see that your cell A, I will call it as a node A, and cell B I will call it as cell this A here we are not representing in terms of A, we are representing in terms of 1, right? Cell 1, and we have cell 2, that is nothing but this is your cell 1 and cell 2, and we have your cell 3. And according to this diagram, cell 1 to cell 3 there is a connectivity. So cell 1 to cell 3 there is a connectivity, and cell 2 to cell 3 there is a connectivity. Yes, cell 2 to cell 3 is a connectivity. Of course, here it is going to what? It is going to Y as an input. Here it is coming as what? A and B as an input, and here I am coming as what? Your D and C as my input. So, but we are not going to considering this, right? As a graph we are not going to considering this, but we are considering only the number of cells, and according to the cell connectivity we just make a connections over here. Now we are representing in terms of graph the same logic circuit. What is it available on the left hand side? It is represented in terms of the graph on your right hand side. Okay. So what we can able to understand over here, so the graph theory here we are trying to accept it in terms of converting your given any complex circuit into a very simpler form of a graph. Once you convert your logic circuit into a graph, then it is more easy for us to handle the graph in more effectively in terms of any kind of reduction or in any kind of identification of factors of any VLSI, the factors in terms of your power, the factors in terms of the speed, the factors in terms of the delay. So we can able to measure any factors of this VLSI factors in more simplified way in terms of by means of implementing by means of your graph. And also all we should remember, the graph is one type of data structure. It is more effective usage of data structures which we can use it over here to verify this functionality in more effectively, right? And what is this graph is indicates actually, what graph says that. So if I am going to say a graph, let me take a simple graph. I am just plotting a simple graph. If I take a graph, let's say it's A, B and C, I am just saying that, and this is going to be a simple graph, we can say that. In general, the graph can be represented in terms of what G of V comma E we can say. That is a simple representation of a graph. So where V is nothing but a vertices, or we can say nodes. V is nothing but a vertices, we can say the nodes, or we can say that it's nothing but vertices. So the V can be written as set of number of vertices. So here the number of vertices are what? A, B, C. We can say that A comma B comma C, or in other terms we can say that it can be written as VA comma VB comma VC can be a vertices, right? So it's a set of vertices. So in other terms we can say that V is belongs to what? V is belongs to VA or VB or VC, we can say it's going to be a vertices. This is what the way we can able to represent the graph G of V comma E, and followed by we are representing the vertices. So how we can represent the edges over here? It's not only, now we have represented only the vertices, right? A, B, C we represented. So next we should represent our what? We should represent our edges. So these are the edges. We can say that edge E1, E2, E3. So we are representing what? We are representing edge, E edge. So that is nothing but E. So what is edges indicates? Edge indicates what? The edge is indicating that the connectivity between two nodes or two vertices, we can call it as what? Edges. So accordingly, this is the edge which is running between what? EAB, and this is the edge which is running but what? Your ECB, and this is nothing but EAC, we can say that, right? Means normally we are representing your edges in terms of what? EIJ format. EIJ format means we can say that E, capital E is equal to the edges of the graph. So how we can able to represent that? So the capital E is equal to set of E, I, J, we can say. So I value is equal to 0, 1, 2 up to n, or we can start with 1 also, no problem. J value is equal to 1, 2, 3 up to n. So what is this VA and VJ? This VA and VJ, this I and J is indicates what? This I and J is indicated vertices. So we can say that the E can also be written as, it can be written as in terms of E, I, J, where this Ij for all, we can say that vertices, for all Vi comma Vj is belongs to capital V, right? So this is what the way we can able to represent your edges, right? So we have seen that how to represent the vertices, and we have seen that how to represent our edges to be write it over here. Or simply peoples also we can written as, we can say that edge is equal to here, since it is going to be EAB, we can say that EAB comma ECB comma EAC can also be right in terms of your edges of a given this particular graph. So this is what the way we can able to represent the graph, a simple graph. So in terms of the vertices and in terms of the nodes, right? Now we try to understand what are the different types of graphs are available. Okay, there are 10 types of graphs are available. Let me see one by one what are the different types of graphs are available. Let I assume that the first category of the graph is nothing but what? A null graph. The first category of the graph is nothing but what? A null graph. What is null graph says that? The null graph says that this is called, let's say for example, node A, and this is node B, and this is node C, and this is node D is available. So all of us know that the graph can be represented in terms of G of V comma E. Am I correct? But in the null graph, we can represent this in terms of a G of V, means here there is no edges. There is no edges of your graph. Means the graph will consist only the vertices or the nodes, and the graph will not contain any edges. So if you found any kind of graph which holding only the vertices, we call that as a null graph. And the second category of the graph is nothing but trivial graph. Okay, the second graph is nothing but what? A trivial graph, we can say that. A trivial graph will consist of only one node. The trivial graph will consist of only one node will be present, or there will be only one vertices will be present. That is called a trivial graph. Let's say for example, it will consist when there is only one node is available. I have written only one, so it doesn't contain any other nodes over there. So this we can call it as what? A trivial graph. Followed by the third category of the graph is available, that is nothing but non-directed graph. Non-directed graph, or we can say that this is undirected graph. Undirected graph. Let's say I have the nodes A, 1, 2, 3 and 4, and there is a connectivity between 1 to 2 and 2 to 3, 3 to 4 and 1 to 3. If you look at this, of course this consists of vertices called 1, 2, 3, 4, and the edges are available. Let's say for example this is E1, this is E2, this is E3 and this is E4. So edges are available E1, E2, E3, E4, we can say that. But see that there is no any directions of your edges over here. Means it's not indicating that whether the directions of the moving of your edge, like whether whether the edge is connected between either whether edge is moving from 1 to 2 or 2 to 1, it both are, we can take it granted, because there is no direction is not indicated over here. In what direction the edge is moving, that is not shown over here. Either I can consider this edge 1 is connecting 1 to 2, or I can also say that it's connecting 2 to 1. Both can be representable since there is no direction is indicated. Same way if we are going to consider this E4, same way if we are going to consider this E4 here, the E4 can also tell that this is connecting 1 to 3, at the same time it's connecting 3 to 1, so that the moving direction is missing. So in any graph there is only nodes are available and edges are available, and if you are not finding any kind of the movement of directions, so that kind of graph we used to call it as your undirected graph, or we can call it as your non-directed graph. That is your third category of your graph. Let's see that what is the fourth category of the graph, that is nothing but directed graph. That is nothing but what? A directed graph. Let me take a simple graph over here. So 1, 2 and 3 and 4, and I just plot the direction likewise. Okay. The same graph which we have taken in the last example, we have considered over here the same graph, but here we can see that the graphs which consist of edges, and the edges are indicating that in what direction that particular edges are moving. So this is called a directed graph. So in this case also we have the vertices called V1, V2, V3, V4, and here the E is nothing but what? E1, this is E2, this is E3, this is E4. We can say it consists of E1, E2, E3, E4. But if we take E1, the E1 is always represents that the edge is connecting between only 1 to 2 and the edge is not existing between 2 to 1. Of course, see, the edge is existing between 1 to 2, am I correct? Then 2 to 1 is also okay, fine, but if there is no direction. But what this direction says that this edge is going to be existing between 1 and 2 only in direction of moving from 1 to 2, not from 2 to 1. That is the meaning. Same way, when you are going to take this particular H2, it is representing that the H2 is moving from the direction of 2 to 4. That is what it is indicate. It is 1 to 2. And what about the edge E3 is indicate? The edge E3 is indicate that the edges is moving from 3 to 4. And what our E4 is indicate? The E4 is indicate that the edge is moving from 3 to 1. So this is totally different when I am writing 1 to 3. So we can't take these both are same. So this is not going to be applicable in this particular case. So in this case we are just telling that specifically in what direction that particular edges are moving. That is called, we can call it as your directed graph. Okay. And there are one more category of graph is available, fifth category of graph is available, that is nothing but connected graph. It's called connected graph. Just you can say a connected graph. Let I assume that here I have the same 1, 2, 3, 4. I am just connecting the edges like this. Okay. So it is called your undirected graph, correct? And let's say for example I have like for example 5, 6, 7. This is another one graph is going to be available separately. Let's say there is an edge is existing between this 4 to 6. So before, when 4 to 6 is not available, this is indicating a graph 1, this is indicating graph 2. But if you are going to connect, there is one edge between this particular graph 1 and graph 2 here, or I can able to connect, if I connect this particular edge between this 1 to 5, or I can able to take the edge from this particular graph 1 to any other node of the graph 2, we can call this particular graph as what? A connected graph. Means if edges exist between two nodes of an individual graphs called connected graph. Means if I remove this particular edge, then this graph is become two separate graphs. If this particular graph, if this particular edge is existing, then it is not a two different graphs. Instead we can call it as a single graph, but this graph we can call it as what? A connected graph. That is the meaning. Now I can able to understand, now we can able to understood what do you mean by disconnected graph. We can able to easily understood what do you mean by disconnected graph. Disconnected graph. What this disconnected graph says that? The disconnected graph says that if I am going to remove specifically one particular edge on this particular given graph, then the graph should be converted into a two separate graphs. If we can, that particular graph can form two separate graphs. If I am going to remove that particular edge, then we can call it as what? A disconnected graph. Now this is going to be a disconnected graph. So where in disconnected graph we can able to represent multiple graphs in separately, not in a single graph. So that is the difference between your connected graph as well as your disconnected graph, we can say. So followed by we can able to have an acyclic graph, cyclic graph. It can be a seventh type of your graph, cyclic graph. Cyclic graph. So what cyclic graph says that, let's say for example A, B, C. Now from A to B, it's a directional graph, right? A to B and B to C, and we can say that C to A. Okay. So let I assume that I am starting from the A node. According to directional, it is going to B node. From B to it is coming to C node, and from C it is coming back to A node. The cyclic graph will have either directed edge or it can will have undirected edge, which may connect the starting node by following a loop or a path. Means we are starting from A, and from A to go to B, and B to is coming C, and C to is going to A. So we started from A and we are just reaching back to B. So the graph will have a cycle, or the graph might have a loop where we can able to start from one node and we can come back to the same node in terms of the loop or in terms of the path which is going to be getting existing. That is going to be a cyclic graph. Then what do you mean by acyclic graph? Just opposite to that. Then what about acyclic graph says that? The acyclic graph says, what is the acyclic graph says? Let's say for example A, I am going to B, I am going to C, and I am going to D, and I am going to E. Okay, so let's consider this is going to be the graph. Then this is also a directional graph, and let's say I am just starting from A, node A to node B it's going, node B to node C, node C to node D, and node D to node E, but this node E to node A is not going to be possible. So means we can't able to reach the starting node, we can't able to reach the starting node by means of either directed edge or by means of your undirected edge. So if you are not able to reach out your starting node if in your graph without existing of any path or the loop, then that particular graph we can use to call it as what? An acyclic graph. And this is also another one type of your graph architecture, graph structure. Then followed by, let me see the ninth type of graph, that is nothing but biparty graph. So when you are going to see the biparty graph, it's almost like your disconnected graph. There will be a two set of graph will be available over here. Let's say for example A, B, C, D, and here I have E, F, G, H. See that there are two set of vertices are available, or two set of nodes are available on your left hand side as well as your right hand side. And if you, let's say for example, if this is going to be considering as a graph 1 and this is going to be considering as a graph 2, look at this particular graph 1. What is this particular graph 1 says? That this particular graph is saying that I have 4 nodes. Am I correct? This particular graph 1 say that it having vertices, that is nothing but we can say that VA, VB, VC, VD. Am I correct? And here also we can say that G2 is nothing but vertices I have, there is nothing but VE, VF, VG, VH we can say. What about edges over here? Edges are null. What about edges here? Here edges are null. I am just talking about only this particular graph 1 and graph 2. And what type of graph it is? If the graph any graph which consisting only the vertices and there is no edges are available, means what type of graph it is? It is called a null graph. It is called a null graph. So we can say that there are two null graph is available. So G1 and G2 both are representing what? A null graph. What do you mean null graph? Null graph will consist only the vertices and there is no edges. But what bipartite graph say that if you are going to consider two null graphs and if there is edges existing between one null graph to the another null graph, then we can call that particular graph as bipartite graph. Are you understand? If the edge can be existing between one null graph to the another null graph, then we can call that particular graph as a bipartite graph. It means there is no edges are going to exist between G1 among G1 and there is no edges going to be exist between the nodes which is among G2. Instead, the edges will be present between your G1 to G2. Means we can have the edges can be connected like this. The edges can be get connected like this. So this particular graph we can use to call it as what? A bipartite graph. So look at it very closely. These so called whatever the nodes are available over here, so called whatever the nodes are available here called A, B, C, D, it doesn't connected with any edges. At the same time, your so called nodes of your E, F, G, H on your G2 doesn't connected with any kind of edges, but instead the edges are existing between two different null graphs, or they say existing between the nodes of your two different graphs G1, G2. That is called your bipartite graph, we can say. Okay, and that next category of your graph is nothing but 10th one. The next category of graph is nothing but your complete bipartite graph. Okay, the next category of your graph is nothing but a complete bipartite graph. So what the complete bipartite graph says that here also let me assume that I have 1, 2, 3, 4, that's G1, and here 5, 6, 7, 8 nodes as G2. As I said, G1 is nothing but set of V1, V2, V3, V4. Here G2 is nothing but, your V, capital V here, means vertices, right? Means vertices. Same way here also the capital V, vertices equal to V5, V6, V7, V8. And here also edges are null. Null means what? There is no edges. Here also edges are null. Am I correct? So both cases the edges are null over here. But here what we can see that according to the previous bipartite graph, what is the bipartite graph says that previous type means there is no edges between the vertices among your null graphs. Am I correct? You are here the G1 and G2 both are null graph. Null graph means what is the meaning? No edges between nodes of graph. It is called null graphs. Okay, there are two null graphs. But what is complete bipartite graph in the sense? According to the definition of bipartite graph in the sense, like the edge should be present between one null graph vertices to the another null graph vertices. Means like this. That is a bipartite graph. But complete bipartite graph in the sense, the node of one node of your one node of a null graph must have a connectivity or must have an edge between the other all nodes of your another null graph. Okay, means the edge should be exist between one node of your null graph should be exist between all other nodes of your null graph. Means like this 1 2 3 1 to 5 1 to 6 1 to 7 1 to 8. Means from the one node of your null graph and it should have the edge should be exist between the all other nodes of your other null graph. Say if we take 2, if I take 2, let us take say a different color. If I take 2, we may have the connectivity like this, right? And if I take 3, and these might be the connection can be existing between your 3. If I take 4, then we can say that these might be the connectivity it's existing between 4, right? So this is called your complete, this is called a complete bi-party graph. Right, according to the definitions, like if I take one particular node of one null graph G1, the edge must be exist between the all other nodes which is present on the G2 or in the all other graphs of your null graph. That is called your a complete bi-party graph, we can say, in your graph theory, right? And finally, the final category of the graph is, we can call it as what, the 11th one, we can call it as a hypergraph. Hypergraph, we can say that, right? Let's say for example, we can take it as a circuit, any circuit. Yeah, we are taking this as a complete circuit, one example circuit. Let's say for example this is 1, this is 2, this is 3, and this is 4, this is 5, and this is 6. Okay, and let us assume that this is okay, let us assume that this is taken from here. So we know how to convert this particular given circuit into graph. So let me try to convert into a graph now. So how we can able to convert into a graph? We are not going to worry about what is your inputs nodes, what is your input lines over here, output lines over here. Let me consider only your cells. So we can say that cell 1 is available, cell 2 is available, cell 3 is available, cell 5 is available, and cell 4 is available, cell 6 is available, right? So we can say that 1 to 3 there is a connection, 1 to 3 there is a connection, 2 to 3 there is a connection, and 3 to 5 there is a connection, 3 to 4 there is a connection, 5 to 6 there is a connection, and 4 to 6 there is a connection. And also we can see that 1 to 5 there is a connection, right? So now these can be represented in terms of your hypergraph, means we can able to say that it is going, this is a normal graph, this is generally we to represent like this, it is going to be a normal graph. Now hypergraph can be represented by the way, see that this is 1 to 5 is get connected by this particular point. So we can say that this edge can be taken from tapered from here, this can be connected to 5 like this. So the so called edge, let's say for example if you are going to make a mark of the edge over here now before making this, so this, let's say for example this is E1, okay, let me take the edge in the different color. So it is a different color. So let I take, if these are edges, if this is my E1, okay, and if this is my E2, and this is my E3, and this is my E4, and one more thing, this is my E5, and let's say this is my E6, we may say. So this is E1, we can say, we will just used to say it's a E1. So from here it is tapped, it is going to be getting connected. So this edge I won't name it as your some other E, we can name it as what, E1, we can say that. Am I correct? So because it is tapped from E1. So how we can represent the hypergraph in terms of your edges? Likewise, we can say that 1, 2, 3, 5, 4, 6. We can say that this 1 to 1, your 1, 5, 3 is connected with the 1, 5, 3 is connected with the edge 1. So we can say that 1, 5, 3 is connected with the edge 1. So 1, 5, 3 is connected with what? Edge 1. Okay. And 5 and 6 is connected with what? Your edge 5. So 5 and 6 connected with what? Your edge 5. And 4 and 6 connected with what? Edge 6. 4 and 6 connected with what? Edge 6. And 2 and 3 is connected with what? Your edge 2. So 2 and 3 is connected with what? Edge 2. We can say that. Again 3 and 5 can be get connected between what? The 3 and 5 can be get connected with what? Your edge number 3. Edge 3 we can say that. So in hypergraph we can see that how we can able to overlap your edges, or how we can able to make use of the common edges to connect your multiple vertices. That is what the way the hypergraph is going to be getting represented over here actually. Right. So the most of the cases when we are going to handling with our VLSI circuitry, this hypergraph will be more useful to represent our graphical representation. Right. So that's all in this today's session. In today's session we have seen that why we are using the graph theory. So all of us now you understood that the graph theory, we used graph, why? Because to be simply to represent the VLSI circuit in a more easiest way by means of your nodes and edges. So the cells of the logic gates can be represented in terms of the nodes or the vertices, and the interconnections which we are available between your cells can be in term represented in some of the edges actually, right? And one more point which we have, which we just before closing the today's session, let me have one more point is nothing but what is the representation of a graph into matrix? Okay, representation of graph into matrix. Representation of graph into matrix. That is one more topic is missing in the today's session. Let's say for example there is a graph A, B, C, D. So manually by seeing that we can able to easily understand there is a connection between your A to B and B to C and C to D and D to A. But how we can able to make sure to the system has to be get understand, we can make that the system to be understand about this graph by means of writing the connected matrix. By means of representing what? A connection matrix. How we can write a connection matrix? We can connect the connection matrix like this, where we have 4 nodes. The connection matrix can be written between your nodes to nodes. So our vertices to vertices. So here the n is indicating what? Your vertices are the nodes, we can say that. So we have 4 nodes A, B, C, D, and here also we have 4 nodes A, B, C, D. We can close it. So A to A there is no connector. So the A to A there is no edges are existing because it's self representation, it is not available. So we can write 0. A to B there is a connection. So we can write 1. And A to C there is a connection. Is there any connection is available? No. There is no direct connection is available. A to C is 0 because connection matrix is represented in terms of the what direct edges are available between the 2 nodes. Okay. A to A there is no nodes and there is no edges. A to B there is a edge, direct edge is present, there is 1, and A to C there is no edges present, 0, and A to D there is edges present, 1. Okay. Then what about B to A? B to A there is edges present, because these edges can be get considered, we can write 1. B to B there is no edges not available, 0, and B to C there is edges available, 1, and B to D there is no edges available, 0. Okay. C to A there is no edges present, and C to B there is edges present, C to D there is a presence, and C to A there is no presence of edge, 0. Same way we can write D. D to A there is edge is present, and D to B there is no edge is not present, there is no direct edges, and D to C there is edge, and D to D there is no edge actually. Oh, here C to C is no edge, right? C to C there is no edge, correct, and C to D there is edge, so here it should be 1, this should be 1, it has to be get corrected, this has to be 0, there this has to be 1. So if you look at this connection matrix, this the diagonals of your matrix has become 0 because there is no any self loop is not present. So if there is no self loop is not present on my particular given graph, the diagonal element of your connected matrix is going to become 0, and followed by wherever the edge is existing between one node to another node, so we can write 1, right. So this is called a connected graph, to represent easy way of representing your graphs into the mathematical formula, a mathematical format. So this is applicable when we are going to have an undirected graph. Let's say for example how we can able to rewrite this particular connected matrix for the directed. Let's say now we can able to change the directed. So I am changing to this blue color. Let's say for example this is my direction is given over here for this particular. So how we can write the connection matrix for the directed graph now? So we can write the connection matrix here in terms of what? In terms of A, B, C, D, and here also we can write in terms of A, B, C, D. So A to A there is no connectivity, A to B yes there is a edge is existing because the direction is going like this, so we can say 1. And what about A to C? There is no edges are available, direct edges are available, 0. And what about A to D? Previously A to D we are writing 1, but now we can't able to write 1. Why? Because like now there is no A to D, there is no arrow is not available, only D to A is available, so it is become 0. Okay. So now what about B to B, B to A? B to A there is no B to A edge is not existing, only A to B is available because the direction is out towards from A to B, there is no directions of towards your B to A directly, so we can say B to A is 0, B to B is 0. And what about B to C? F, of course there is a connection is available B to C, so we can write 1. And what about B to D? There is no direct connectivity, so we can write 0. And same way what about C to C? There is no availability of C to C, 0. And followed by we can write that. And what about C to B? C to B is also 0, and C to D is 1 because there is edge, and C to A is not available, so we can't able to. So C to C is 0, and C to D is nothing but what? There is a 1, correct? Yeah. So C to A is not available, 0. C to B is not available, 0. C to C is not available, 0. C to D is available, 1. Okay. Now same way D to A. D to A, yes there is a connectivity is available, so 1. And D to B there is no availability, 0. D to C there is no availability because the arrow mark is in opposite side, 0. And D to D is 0. So this is what the way we can able to write a connection matrix if there is a direction is going to be getting existing. And when we can write A to A 1 or B to B 1 or C to C 1 or D to D 1, if there is self loop is getting existing. Self loop means what is the meaning? If a circuit holding like this and the same way it is holding like this, same way it is holding like this. So how we can able to rewrite this particular matrix? So here this is a directed, right? So it's a directed, right? So A to A the connection is available 1, I will say. Why? Because there is edges available, A to A there is edges available, so I can replace in terms of 1. And same to way B to B is also available, I can replace in terms of 1. And C to C is also available, we can replace 1 to in terms of 1. Okay. So this is called the self loop, where it's starting from the same, it's starting from one node and is ending with the same node. Means starting from B and ending with the same B. It's called self loop. So whenever the self loop is available, we can make that your diagonal matrices become 1 as in a connection matrix. So this is called a connection matrix of a graph. Okay. And one more matrix is going to be, we must know about it, that is nothing but weight matrix. That is nothing but weight matrix. weight matrix for either for a connected graph or either for not connected graph, either for directed graph or undirected graph, either for directed graph or undirected graph. Okay, so let's say for example A, B, C, D. This I am going to consider for the undirected now, because directed we can, you know how to write it. Let's say this is going to be 5. The weight of this edge is 5. The weight of the edge is 3. The weight of the edge is 2 here, and the weight of the edge is 1 here. Previously, when we are representing the graph, we are not representing any terms of any weights over there, but here we are introducing the weight. So every edge having a weight. So what is this weight is indicating here? What is this weight is indicating here? What is this edge weight is indicating? So all of us know that from where we are getting this graph, we are getting the graph from our VLSI circuit. Am I correct? We are getting from a VLSI circuit, or we are getting from any kind of any input circuit we are converting into a graph. We know how to convert it now, right? So now what is weight is representing in terms of over here, whether weight is a current or weight is a voltage, or what is this actually? So the weight can be electrical parameters of circuit, or the weight can be a physical parameters of a circuit. It can be anything. The weight can be represented in a graph over here. Since we are converting, or since we are generating the graph from our given circuit, the weight can be representation of your electric parameters, or the weight can be representation of your physical parameters. It can be a power. The weight can be a power. We can able to represent over here in terms of electric parameters, or the weight can be a physical parameters like your wire length. Like your wire length can also be your weight. We can say that. Am I clear? So we are just clarifying what you mean weight. Now how we can write the weight matrix over here now? So let's say for example, as like the previous, we can write the matrix A, B, C, D, A, B, C, D. And since it is a undirected graph and there is no self loop is available, we can directly write that the diagonal values is going to become 0 because there is no change on that. Now we can write A to B. So what is we can write in terms of your A to connection matrix now? In connection matrix we can write when A to B, yes there is edges existing. If it is connection matrix we will write 1, but here we should not write 1. Instead what we should write? We should write the weight of that particular edge. So we can write 5. What about A to C? A to C is 1 because A to C is 1. What about A to D? A to D value is 0. Right? So instead of writing a connection matrix as like 1, we are writing the weight. What about your B to A? B to A there is no, yes there is a connectivity again, it is called 5 because it is called the undirected graph, right? And B to B 0 and B to C there is no connectivity, and B to D we can write it is 3. Then what about your C to A? C to A value is 1 because there is existing 1, and C to B value is not available, and C to D value is available, that is 2. Weight of the matrix, weight of the edge, right? And D to A value is 0 and D to B value is 3 we can say because 3 is available, and D to C values we can write 2, right? So instead of connection matrix we are writing weight matrix, means we are replacing the connection matrix 1 with the weight of the edges which is present. And I strongly believe that you know how to write for your directed graph. We written for this particular for the undirected graph, and we know how to write for your directed graph. So this is the way at which we can able to convert your given circuit into a graph. And by the way, by means of by following different types of graph, we can represent by means of any one of the graph methodology, and followed by we can able to represent our connection matrix as well as the weight matrix that will be more useful for us to go for a further estimation for a given circuit. Thank you so much for the session.